once we're able to compute antiderivatives using integration by substitution, the next step is definite integrals. Let's recall the first fundamental theorem of calculus. So I'm going to have function little f continuous on the closed interval ab. Capital F is going to be an antiderivative of little f. So that just means the derivative of capital F is little f. Then if I take the definite integral from a to b of little f of x with respect to x, so remember that's just the net area between the function little f, the x-axis between the points a and b. It's going to be equal to capital F evaluated at b minus capital F evaluated at a. Now, for our first method, it's going to be business as usual. So if I want to compute a definite integral using integration by substitution, we just work out our indefinite integral or antiderivative, and then just use our procedure from first fundamental theorem of calculus. So let's look at an example. So I'll have definite integral from 0 to 1 of x times x squared plus 1 to the 5th power dx. Now, here I'm just going to find an antiderivative, evaluate the endpoints, take the difference. So we're going to look for antiderivative capital F. So what do I do? We're going to do integration by substitution. Okay, I know I use that because we have a composition in the integrand. Okay, it's going to be the x squared plus 1 to the 5th power. I'm going to set u equal to the inside function, which is x squared plus 1. Take the derivative of both sides with respect to x, then move the dx to the other side. So I'll have du equals, okay, x squared plus 1 goes to 2x, the dx goes to the other side. So if I solve for dx, I get du over 2x. We substitute. So we're only going to do the antiderivative here, or the indefinite integral. So the x stays where it is. I'll have u to the 5th, and then dx is equal to du over 2x. The x's cancel, the half pulls out, and then we note whatever's left over is in terms of u. So I'm going to take an antiderivative with respect to u. So we get that by adding 1 to the exponent and then divide. So we'll have 1/6 u to the 6th, multiply by a half. We add our constant. And then since my final answer has to be in terms of x and not u, we put back in the x squared plus 1. So our antiderivative that we're going to use to calculate our definite integral is going to be 1 over 12 x squared plus 1 to the 6th power. And then we have a plus a constant, but that'll go away when we take the difference. So we don't have to worry about this first term here. Now, we put our 0 and our 1 in. Okay, so that's for our definite integral. So f of 1, that's going to give me 1 plus 1 to the 6th power, so I'll have 2 to the 6th. Then if I put 0 in, I'm going to have 0 plus 1 to the 6th power, which is just a 1. 2 to the 6th is 64, so I'm going to wind up with 63 over 12. 3 divides into the top and bottom, so I'm left with 21 over 4. Another way to get our definite integral, change of variables. So the idea here, we're going to proceed as usual with integration by substitution. Only change is going to be, when we get to our antiderivative in terms of u, we're not going to go back to the x variable. So the idea is going to be, we're going to take everything from an integral in x, convert it completely into an integral in terms of u. The only catch, the limits of integration, which are in the x variable, we want to move over to the u variable. The way we do that is by using the substitution. Let's take a look. So we have our definite integral from before. So we're going from 0 to 1 of x times x squared plus 1 to the 5th dx. We proceed as usual. I let u be equal to the inside function x squared plus 1. So du equals 2x dx, or dx equals du over 2x. And then the new part is, I'm going to put 0 and 1 into the u function. So if I put 0 into here, we're going to get u equal to 0 squared plus 1, or 1. So it's going to be the new lower limit. And then u of 1 is going to be equal to 1 squared plus 1, which is 2. And that's my new upper limit. So we change everything over to u, and what do we get? Well, from before, we had 1/2. Okay, now it's definite integral from 1 to 2 of u to the 5th du. Same work gives me 1/12 u to the 6th. We evaluate at 1 and 2. It's going to give me 64 minus 1, and then there's a 1/12 in front, and I get the 63 over 12 that we had before. Let's do a change of variables using trig functions. So we'll have definite integral, so we go from 0 to pi over 4, tan of x, secant squared of x dx. So you'll note we do have a composition here. Okay, that's going to be secant as the inside function of the square function. But you'll also note we have our special case where I have a function, tangent of x, times its derivative. So I can use a u substitution here without a composition. So I'm going to let u be equal to tan of x. Then du is equal to secant squared dx. Okay, derivative of tangent is secant squared. So you'll note this last part here is just du. So I really have u du when we do our substitution. We change our limits over. So our first limit's 0. So I'll have u of 0 is equal to tan of 0. Okay, that's going to be sine over cosine, the sine of 0. Okay, angle 0 is on the x-axis. The y value is 0, so that's going to be equal to 0. Then for pi fourths, u of pi fourths is going to go to tan of pi over 4. Well, that's sine over cosine, and for pi over 4, they're equal, so we get a 1. So our new limits, we'll have a lower limit 0, upper limit of 1. So the new integral, in terms of u, is going to be equal to, okay, we have a definite integral from 0 to 1 of u du. Now, the antiderivative with respect to u, I'm going to have 1/2 u squared. We're going to evaluate at 0 and 1 and take the difference. So I have 1/2, then 1 squared minus 0 squared just gives me a 1/2. So you can check that work by working it out by putting everything back in terms of x, and you'll see that you get the same answer. Here are two examples worth noting. First, the definite integral from -1 to 1, x times 1 minus x squared, quantity squared, dx. We do our change of variables. So I'll let u be equal to our inside function, 1 minus x squared. Du is equal to minus 2x dx, or dx equals du over minus 2x. We change our limits from x to u. So we'll have u of 1 equals 1 minus 1 squared, gives me a 0. U of minus 1 also gives me a 0. So with our change of variables, you'll note the limits of integration are the same. This is not a problem. Okay, we know whenever the limits are the same, we automatically get a 0 out. Here, you're trying to take the area of a line segment going from the graph of the function to the x-axis. So there's no area there. Now, to make sense of that, if you go back to the original function, let's take a look. This is an odd function. So if I take the region from -1 to 1, you'll note, okay, the part that goes from 0 to 1 is going to cancel out with the part that goes from -1 to 0. So we're going to expect a 0 to come out. For the next example, we'll use the same integrand, except the limits will now go from 0 to 2. We do the same substitution. Here, for our limits, u of 0 is going to go to 1 minus 0 is 1. Then u of 2 is going to go to 1 minus 2 squared. That gives me a minus 3. Now, when we put everything over with the change of variables into u, you'll note for our limits, we have going from 1 to minus 3, but 1 is a bigger number than minus 3. So this is no problem. You just use your first fundamental theorem of calculus like you normally would. So what I would do then is, okay, take your antiderivative, put in your 1 and your minus 3, you take the difference, then you get your answer of 28 over 6. Now, if you really didn't like this here, what you could do, okay, we have a rule that says if you want to interchange your limits of integration, you have to introduce a minus sign. So if you were to work that out, you'd still get your 28 over 6.